when we look at this entire unit, guys, come on. Really, we're looking at something that we've already learned. So when we're learning angular motion, this entire unit is really a repeat of the whole semester. You've already learned all of the basics, all of the concepts that we've talked about so far. It's just now we're going to readdress every topic that we've already learned, but now in terms of rotation. So starting from the beginning of the year, we talked about displacement. We talked about velocity. We've talked about acceleration. We've talked about forces. We've talked about energy. We've talked about momentum. I'm also going to tag in here mass and time. So what we're going to do is we're going to take a look at each one of these and how it relates to its rotational analog. So displacement, of course, was delta x. We're now going to be talking about angle, which is, of course, theta. Velocity was v. We're now going to be talking about angular velocity. Angular velocity, which uses the Greek symbol omega. That is totally not a W, it is omega. Acceleration, which is A, is now going to be, there's a whole bunch of these. Angular acceleration, which is marked as alpha, but also centripetal acceleration, which is going to be denoted as A sub C. We're going to talk about torque in place of forces. I have a bad habit of writing torque with a Greek T because its symbol is tau. We are specifically going to be looking at rotational kinetic energy, which has a nice easy symbol of RKE. We are going to, instead of looking at momentum, we're going to look at angular momentum. Instead of, angular momentum is L. Instead of mass, mass is a way of measuring what value or what property in physics. Inertia. So we're now going to look at rotational inertia. Yeah. Rotational inertia is I. And instead of time, we're going to look at time, which is measured in seconds. Thank God time doesn't spin. All right. So what we're going to do is, just like this is laid out from the beginning of the year to what we've covered so far, we're going to start by just looking at these three topics. In this, we're going to call this angular mechanics. It is. Okay. So starting with angular mechanics, one of the things that we're going to recognize is every one of these variables, displacement, velocity, and acceleration, has a rotational analog, angle, omega, and alpha. We can relate the linear value to the angular value through the radius of the object. So linear values are translated to angular through the radius of curvature. Through the radius of curvature. At the top of your PhET sim from yesterday, you were given a handful of different equations. What were they? Not quite. So it wasn't omega. It was omega rather than W. So I'm going to start here with S, omega, and alpha. Okay? Each one of these, oops, I didn't want S, I wanted theta. I'm sorry. So S, omega, and theta. Each one of these is the angular version. S is arc length. We'll get there in a second. It's the same as delta x. So theta, omega, and alpha. These are our angular values. Each one of them can be developed from a linear value by, which part, Connor? Curvature. By dividing the original value by r. So delta x over r, v over r, and a over r. Okay? R is the radius. Theta is therefore going to be measured, and here's where this class gets all sorts of fun, in radians. Omega is radians per second. And alpha is radians per second squared. Yes, r is radius. Okay. Delta x may sometimes be translated for s, where s is arc length. We translate these two in the same way because if we take a circular object and I point, I'm just going to pick out the spot with the masking tape. If I place the masking tape at a certain location here, and I rotate my hula hoop a quarter of a turn, I have a new location on my desk. The distance traveled linearly between here and here on my desk is delta x. That is the same value as from here to here, meaning the arc length around my circle. Okay, so arc length and displacement are exchangeable because they represent the same linear distance. Good idea? Yeah, if I cut the piece off the hula hoop, that'd be delta x as it goes straight. Whereas if I just hold it curved, however far it traveled in space, would be delta x as opposed to if I just tried to like take a string and measure the arc length. Say again? Because then we're working with a parabola and not a circle. Yeah, this is all talking circular mechanics. Oh, right. Oh, we can make it work. All right. So in addition to just being able to translate each one of these to and from linear versus circular, we also have a set of relationships for interchanging between the angular values. Theta being defined as simply angle, omega being angular velocity, is a change in position over time. Now, I want to make sure there's differentiation between regular velocity and angular velocity here. Change in position in terms of linear velocity means where are you physically located. Change in position in terms of angular velocity is what way are you facing. Okay, so if rather you want to define this one as a change in orientation over time or a change in facing over time, those would be appropriate definitions. A change in orientation over time. If you wanted to define a system as if you wanted to define a frame of reference from as outside of Earth, yeah, you could talk about everything on the planet having angular velocity. Right. So it's not about what you're defining as a system in terms of like momentum or energy, but what you're defining as your frame of reference. Okay. All right. So change in theta over t, and this is in radians per second as defined above. Alpha is change in angular velocity over time. Change in angular velocity over time, meaning delta omega over t equals alpha. Okay. Now, when we worked with these in terms of the linear stuff, we found that if we wanted to find how far you went, we needed a special set of equations. Because I can't calculate how far something goes just based off of an angular acceleration equation. And I can't just use change in theta over t if that omega is continuously changing, right? For linear concepts, what did we have to use? Kinematics. So we have a set of angular kinematics that we can derive based off of the definitions provided here and the original kinematics. So we've got V equals V naught plus AT. We've got V squared, squared equals V naught squared plus 2A delta X. Yeah, they're on the AP exam. Yep. You don't need to memorize them. Nope. Delta X is equal to V naught T plus half AT squared. And lastly, delta X is equal to half V plus V naught T. Okay, making a quick substitution for each of these, where I'm going to swap in, let's see here, from our definitions here, I'm going to swap in for V omega R. Look good? See why I'm making that substitution? Because V is equal to omega times R. So omega R equals omega naught R plus, let's see here, alpha R times T. Simplifying, what do I get? So you'll notice this is simply the exact same equation with different letters. Okay, and the same happens with each of the following three. So I get omega squared equals omega naught squared plus 2 alpha theta. I get theta equals omega naught t plus half alpha times squared. And I get theta equals half omega plus omega naught t. Go ahead, Habiba. Yeah. Okay. So what I've developed here is a set of equations that tell us, well, the relationship between orientation, theta, how fast you're spinning, omega, and how fast you're changing your rate of spin, alpha, and time, that look identical to the kinematics that are listed right above them, which would represent their linear values. So really what we're pointing out here is that the math is all the same. It's just now we're talking about how fast you slow down or speed up when spinning. Okay? So if we've got a question here of a merry-go-round spins for 30 seconds each ride. If it takes 15 seconds to speed up to max speed or max velocity, what is the, let's say, or sorry, not what is the, how many times does it rotate? How many times does it rotate? If it accelerates at, and now I need to pick some kind of reasonable value here. I'm going to go with 0.1 radians per second squared. Okay? This is really just the same as solving a one-dimensional kinematic problem. I just need to list out my variables, convert if necessary, pick an equation, solve. So whereas I used to write delta x, v, v naught, a and t, I'm now going to write theta, omega, omega naught, alpha, t. Theta, we're trying to find that. We want to know how many times it rotates. Omega, we don't know what its max speed is. Omega naught, well, we know that. That's 0. Because a carousel or a merry-go-round starts from rest, correct? Okay, alpha, 0.1, and t, 15 seconds. Now, if I want to find how many times it rotates, all I've got to do is use theta equals omega naught t plus half alpha t squared. Omega naught is 0. Theta is now equal to half 0.1 times 15 squared. So half of 220 or 22.5, so 11.25. Radians. So how many times does it rotate? I've got to divide that by 2 pi. Oh, I see what you're saying, yeah. How many times does it rotate if it... So this is how many times it rotates to speed up while speeding up. And then if we want to know how many times it rotates during that remaining 15 seconds, let's assume that it's at its max speed for the next 15 seconds, we need to find what that max velocity is. Sure. This is in radians, and the question is, how many times does it rotate? So number of rotations is 2 pi radians, or sorry, one rotation is 2 pi radians, right? So if I've got that it goes 11.25 radians, and I'm going to convert that to rotations, 2 pi radians to 1 rotation, and I know how many times it rotates during that period of time. Okay. Yep, 2 pi. Right? 2 pi to a circle. 1.8, you said? Okay. Marvin, you had a question.
Okay, so will these equations be given to these all?
Angular acceleration and centripetal acceleration. Angular acceleration, as defined up here, is simply a change in angular velocity over time. It's how fast your spinning is speeding up. Okay. However, let's take a scenario where you're spinning the same rate, or you're driving around the circle at a constant speed. Or let's even just take our merry-go-round from this problem and find what its maximum velocity is real quick here. So we found that alpha was 0.1. Let's find an omega final, where omega is equal to omega naught plus alpha time, also read as omega is equal to omega naught plus fish time.
Alpha fish.
0.1, 15, plus 0 equals omega. So we're going to find that omega final is equal to 1.5 radians per second. Correct? Okay. The merry-go-round reaches this speed. Is the merry-go-round accelerating for the next 15 seconds as it is going, or as you are going around on it? Why do you say yes? Right. Everyone on that merry-go-round is still accelerating because they're changing direction. So you can't, I mean, if we're saying we're going to constant angular velocity, your angular acceleration is 0. Okay? But that doesn't mean you're not accelerating. You have to be accelerating in order to change your direction. This is where we see centripetal acceleration come into play. Centripetal acceleration is the acceleration that acts inwards on a circle that causes an object to continue in circular motion. Let me rewrite that. Centripetal acceleration is the acceleration that acts on an object, holding it in circular motion. An object holding it in circular motion. Okay. Centripetal acceleration is thereby calculated as v squared over r, or substituting in our definition from omega as v being omega r, AC is equal to omega r squared over r, showing that omega squared r is the centripetal acceleration. AC equals v squared over r. WR squared divided by r, which equals omega squared r. Okay, so on our merry-go-round, you are accelerating towards the center of the merry-go-round at all times. How many of you on yesterday's simulation noticed that the green arrow, I believe it was the green arrow, pointed mostly towards the center at all the time? Was it pink? Okay, it was pink. So the pink arrow pointed inwards towards the center of the circle. That was a combination of your tangential, linear, straightforward acceleration and the centripetal acceleration. If you had the disk rotating so that it was rotating at a constant angular speed, then your pink arrow pointed directly inwards at all times, showing what the centripetal acceleration was at all times. Anytime that pink arrow pointed all past the center of the circle, it was because you were speeding up at the same time. You were going faster and faster as you were spinning. And that pink arrow was showing us a total acceleration, where it was calculating the addition of your linear acceleration and your centripetal acceleration added as vectors. So if we had our circle and you were spinning this way, and first of all, did anyone have the sound on when they got the ladybug going?
No.
Well, you guys missed out. And it was like, yeah. So we have our ladybug, and the ladybug experiences a force acting, or acceleration acting this way. This acceleration that it was displaying to you was a combination of the centripetal acceleration, A sub c, and its tangential acceleration. And I totally can't draw. This is so a right angle. Yeah? Uh-huh. This one here that I have marked with the angle. Okay? Where this one here would be your straight line acceleration, A. Or A tangential. So your acceleration this way, AT. The idea that if you were to, at any point, just jump off the spinning disc, that would be your acceleration forward. Okay? There are three. I can zoom in. There's linear acceleration, there's angular acceleration, there's centripetal acceleration. Linear and tangential are the same idea. It's the acceleration we've been working with all year. Centripetal acceleration is the acceleration that acts towards the center of the circle. Angular acceleration is how fast you speed up your spinning. Linear is how fast that translates to, like, let's say you measured your velocity right now. You went around the circle once, you measured your velocity again, and your velocity was higher. That would be, there it is. Your change in velocity between those two identical points over time would be your linear acceleration. Hey guys. Yeah. Far left, this piece A sub t, same as this one. They are your tangential acceleration, your linear acceleration.
Is that dot over the middle of the circle?
Yeah.
No, I'm
A sub c is this bottom one, and alpha is here. Those are the ones I have labeled. Yeah. Centripetal acceleration, A sub c. Okay? Now, another term that we run into, centrifugal. Centrifugal is defined as an acceleration or force, this is really an adjective here, that acts outward from a circle, on a circle. And acceleration or force that acts outwards on a circle. All right, so I wanted to make sure we're clear. Centripetal acts inwards, centrifugal acts outwards. Okay? You've probably heard at some point that centrifugal forces are imaginary. Okay? They are, sometimes. Okay? So a centrifugal force is what your non-physics student explains as the force pushing them back into or the force that they feel that's trying to throw you out of the car as you go around the roundabout, which we actually know to be Newton's first law, right? So you drive around a circle, say again, and the force that's trying to throw the bullet out, yeah. It's a weapon used for snaring objects or people, animals. Yeah. Yes, with typically some kind of fiber or leather, yeah. All right, so if we're going to continue with our our car example, car on a circle example. Here's your circle. There's a car. I hear you want to move it up. Right?
Was that you?
All right. So as you're going around the circle, we're going to say V is constant. That means that alpha and A tangential are also constant. Okay? Specifically, because V is constant, these two are equal to 0. However, centripetal acceleration is not equal to 0. Centripetal acceleration is not equal to 0 because if it is, you go in a straight line. Unless defined or specified, any of them. Then it's accelerating. I'm working on it. All right, so if you are sitting in your car, and of course you're sitting in the back seat with a couple of friends, phone, go away. This is Mr. Carney. Yep, will do. Bye. Everett, they want you in the counseling office at the end of class. Okay. All right. So you've got 3 people, guys. 3 people sitting in the back seat of a car. Okay, you go around a curve. What's the obvious thing that you're going to do? Yeah, you're going to lean into the people on the outside of the circle, right? So forces that exist, the centripetal force or centripetal acceleration acts towards the center. What most people perceive as a centrifugal force would throw them to the outside, we know doesn't exist. It's Newton's first law. You're trying to move in a straight line, the car is moving underneath you. However, I'm not saying centrifugal forces don't exist. Because if you're riding with Sophie, she just leaned into you and is trying to crush you towards the outside of the car, right? Okay. She's exerting a centrifugal force on you. Okay? So if we take our 3 people in our car, and let's say this is the center of the circle, and this is the outside. Each person is going to feel a force acting towards the center. This is their centripetal force causing their centripetal acceleration. It's friction of the seat. It's the wall of the car pushing inwards. So I'm going to write these as AC because you're feeling some centripetal acceleration. However, because you're normal human beings, you lean into the person next to you as hard as you can as you go around the circle. This person will now feel a centrifugal force. This person will feel a slightly smaller centrifugal force. And this guy doesn't feel one at all because no one's pushing him out towards the center of the circle. This person's pushing that one out towards the center of the circle, so it experiences, this one's being pushed by this one, so it experiences a centrifugal force. This one's being pushed by this one, so it feels a centrifugal force, but this one doesn't because no one's pushing him. Okay? But they do feel Newton's first law, which is so not a force. No, it's not going anywhere. It could be perceived, which would just be wrong. I mean, it'd be wrong to put it on a free body diagram. Yeah, Connor.
So the person that's not feeling the centrifugal force is pushing, but not.
I mean, by Newton's third law, they're being pushed on a little bit here, but it's still centripetal because it's pushing them inwards. So, as Charlie wants to point out, Newton's third law exists here, but they don't feel pushed this way because of it. They feel pushed more inwards. It's more centripetal force. Yes. Right. So in this scenario here, centripetal with T would be probably friction, maybe a force normal of the wall, but also this person experiences a centripetal force as this person pushes them inwards because they're leaning against each other. Okay. So centripetal, centrifugal, like you said, they're categories or labels we can assign to already existing forces. If we take the idea of the bolas swinging above your head, the string acting on the rocks pulling inwards is centripetal. Okay? Yeah, so basically what she was just doing there. So these would be centripetal forces as they're acting in. I'm sorry, my ability to draw medieval hunting weapons is not up to par. Yeah. All right. Right? Questions about the difference between centrifugal and centripetal? It's always a, I mean, you could say that because it's always pulling in. Yeah. Oh, no, because it can be pushing too, because this person exerts a centripetal force on them as they push them inwards. So it can be tension or compression. Yeah. First one. Yes.
Okay, and then for like acceleration, the tangential acceleration, is that called that because it's like
Exactly why it's called that.
Okay, and that is wait, okay, so centripetal acceleration is how fast?
How centripetal acceleration is how fast your spinning is speeding up. Angular, I'm sorry, did I just misspeak? Which one did you ask me about first? Centripetal is the one that pulls you towards the center of the circle. Angular is the one that's how fast your spinning is speeding up. Tangential is the tangent to the circle. Yes. So again, centripetal pulls you in, centrifugal pushes you out. Angular is how fast your spinning is speeding up. Tangential is that exact arrow at that point in time. She had her hand up. Say that again. You lean outwards from the circle because of Newton's first law, trying to throw you in a straight line. Centripetal acceleration, centripetal force, the force of friction and the wall of your car or your seatbelt hold you in towards the center. When you're just driving around in that circle, unless someone is physically pushing you outwards, there is no force acting out this way. Yeah, nothing's pushing on them, so they're not going to feel it. So this scenario, these two only feel a centrifugal force because someone's playing that game where you push on the person on the outside wall. Which is why we frequently hear centrifugal as an imaginary force. Say that one more time. Newton's first law is often interpreted by people who don't understand physics as a centrifugal force because they think they're being thrown to the outside edge. However, in most situations, except for like these two people, you're not being thrown to the outside edge. And that centrifugal force is simply your brain's poor way of trying to interpret what's happening to you. In this case, it would be like the friction between the tire and the road, friction between your body and the seat, the normal force as you lean against the door to your car. It's any of those forces that are pushing you towards the center or preventing you from just going this way. Oops, preventing you from going this way. Then there's a centripetal force acting. Yes. Hey guys, should be quiet. In. Yep.
How do you define that differently than just having a frame of reference on one of those guys and that guy applying a force straight? Like, isn't that the same thing?
I'm trying to think if I understand the scenario you're saying. So from the frame of reference of the car, of one of the people, that's really awkward because they're changing their velocity. And we only want to deal with inertial reference frames, not with ones that are changing their velocity.